some examples related to the continuous time Fourier series and develop the discrete time Fourier series. So the first example is x of t is 1 for t less than t1, and this is 0 for t1 less than absolute value of t less than t by 2. So whenever you have something x less than 2, so this means either x is less than 2 or this implies minus x is less than 2. So when it's minus x less than 2, you can multiply minus 1 on both sides. So this becomes x greater equal to minus 2. So x less than 2 is simply absolute of x less than 2 implies this is between x is between minus 2 less than equal to x is less than 2. So this is how you expand this absolute of x. If I sketch, so always sketch, so always try to sketch in this course. Engineers should know how to sketch. I have x of t over here, and then I have minus t1 over here, 0 here, t1 here, and then this is centered around t. So this is centered around t. This has the same height actually. It has the same height. This is centered around t. Goes on here. There's a t by 2 over here. There's a minus t by 2 over here. And then this one is over here too. So this is minus t. Okay, this is plus 1. And so here t is between minus t1 and plus t1. T is between minus t1 plus t1. And between t1 and t2, both positive and negative, this is 0. Okay. So now I want to find what is the average value. Obviously, this has an average value. This has an average value over here. And what is this average value? So this is the average value. Average value. And this average value is 1 over t, absolute of t, x of t dt. And this one is 1 over t. This is over one period. So over one period, I can look at this period from minus t by 2 to plus t by 2. So this is one period. I can look over this period. And in this period, my integral is non-zero from minus t1 to plus t1. So minus t1 to plus t1, this is non-zero. And the value from minus t1 to plus t1 is 1. So it's 1 and dt. So this is simply bit this is t, so this is t1 minus t1, so this is 2t1 divided by t. So this is the DC or average value. Okay, and what about ak? So ak is 1 over t, again same thing, minus t1 to plus t1, because it's otherwise 0. X of t is x of t, which is 1. I have e minus j k omega naught t dt, and this is easy to evaluate. This is simply minus e minus j k omega naught t divided by j k omega naught. This is evaluated from minus t1 to plus t1, and when you do that, this is equal to, so when I put plus here in place of t, I'll get a minus here. When I might put a minus, I put a plus, and because of this minus, it becomes a plus. So e plus j k omega naught t1 minus e minus j k omega naught t1 divided by j k. So I'll put j here, and I'll put 1 over k omega naught t over here. Right? So this t k omega naught on this side, and I multiply and divide by 2. So I multiply and divide by 2. So if I do that, this thing here is simply sine. So this is 2 sine k omega naught t1 divided by k omega naught t. Now k omega naught t is 2 pi. omega naught t is 2 pi. So this becomes, so this 2 cancels with this 2, and I'm left with sine k omega naught t1, and you should memorize this result over k pi. And you can see, so this is ak for k not equal to 0. Excuse me. And since this is a square waveform, this is square pulse train, you can see ak is decay as 1 over k. Okay. So let me write here. So ak is 2t1 divided by t for k equals to 0, and otherwise this is sine k omega naught t1 divided by k pi for k not equal to 0. Okay, good. And what is this thing? This one is simply, wait, this thing is simply the samples of, these are samples of envelope, which is 2 sine omega t1 over omega t, where omega is k omega naught, where omega is k omega. So this is a continuous envelope, and we'll see actually when we do the continuous time Fourier transform, this is actually a sinc function. It's sine x over x. So if t1 is t by 4, if t1 is t by 4, or t is equal to 4 t1, this implies omega naught t, which is equal to 2 pi, or omega naught t1, which is equal to omega naught t1, which is equal to 2 pi into t1 over t, and t1 over t is t by 4, so this is pi by 2. Right? So if this is the case, then this implies ak equals half. So 2t1, 2 into 1 by 4. So this is half for k equals to 0. And otherwise, this is, so in here, I can change this one. So I can write this one as sine k omega naught t into t1 over t, right? And this is k pi. So t cancel, this omega naught t is 2 pi, and this t1 over t is a different, takes on different values. So when it's 1 by 4, when t1 over t is 1 by 4, this will become k pi by 2, sine k pi by 2 over k pi, and this is for k not equal to 0. And this implies a naught equals half. What is a1? A1 is, if I put sine pi by 2, sine pi by 2 is sine pi by 2 is 1, so it's 1 over pi. So it's 1 over pi, and this is also equal to a minus 1. This is also equal to a minus 1 because it's a real function. This is equal to the this is an even function. So even function, this is so this is an even function. Your Fourier coefficients are also even, and then a2 is 0, because when I put a 2 here, so this is sine pi, all 2's are 0. So a2k, right here, a2k equals 0 because sine of k pi is equal to 0, where k is an integer, where k belongs to set of integers. And a3 equals sine 3 pi by 2 is minus 1, so it's minus 1 over 3 pi, and so on and so forth. And this is also equal to a minus 3, and so on and so forth. And if t1 by t keeps on decreasing, then we'll see, we will notice AK expand in frequency. AKs expand in frequency. And why is this? Because you are compressing. So compression in time implies expansion in frequency. Expansion in frequency and vice versa. In frequency and vice versa. And vice versa. So expansion, compression in time implies expansion in frequency. Expansion in time implies compression in frequency, and vice versa. Okay. And why is A2K 0? All even components are 0 because if you see here, there is hidden symmetry in this waveform. If I subtract the DC value, then this waveform is actually, this waveform actually comes down. This waveform comes down. So if I subtract the DC value, so my waveform is going to be like this. My waveform is going to be like this. It's going to be like this. So if the waveform is going to be like this, obviously the heights are the same. So this height is the same as this height. So this height is the same as this one. So because it's 8 when T1 by T, T1 by T is 1 by 4, this DC value is half. Since this is half, so obviously these are same. So this is half, and these are exactly the same height. So this one is actually has half wave symmetry. So this one has half wave symmetry. Right? So if this one has half wave symmetry, because if you shift by half the cycle and you flip it, this will be exactly the same as before. Okay. So let's see. Let's look at another example where I think we export this thing. So same waveform, and now we are not going to use the analysis equation, but we are going to use the properties to find the waveform. So again, this one is T1 by T is 1 by 4. So when T1 by T is 1 by 4, omega naught is 2 pi into T1 by T. So omega naught is 2 pi by T, which is equal to 2 pi into T1, 2 pi into T1 over T. When we do that, this is simply pi by 2. So this is simply pi by 2, right? Because T1 by T is 1 by 4. So T is 4. So since T is 4, this is pi by 2. So if T is 4 and T1 is 1, so this goes 1. So 0, 1, 2, 3, and 4. So it's like this. And 0, minus 1, 2, 3, 4. So minus 4 plus 4, 2, 3, 5 goes on here. This is 1. This is x of t. Minus 2, minus 3, minus 5 goes on over here. Okay. Let me redraw this one. Maybe I just wrote this thing. Okay, so this is x of t, and we already know what are the Fourier series coefficients. So f of s, ak, and ak is half for k equal to 0, and this is sine k pi by 2 over k pi for k not equal to 0. So we know this thing. Now we want to, we have another waveform. We have another waveform. This is g of t. So g of t is like this. So we have 0, 1, 2, 3, 4, minus 0, minus 1, minus 2, minus 3, minus 4. It's too close. There's something wrong with this pen. So 1, 2, 3, 4. 1, 2, 3, 4. And this is like this. So this is okay. So this is minus half. This is plus half. This is 1, this is 2, this is 3, this is 4. This is 1, this is 2, this is 3, this is 4. And I think this goes up here, this goes down here, and this is periodic. How is x of t related to g of t? How is, and we want to find the Fourier series of g of t, the Fourier series coefficients. So how is, and we don't want to do the analysis equation, we know this result. So how is x of t related to g of t? So if I shift this x of t by 1, let me see if I can do that. So if I shift this x of t by 1, let me redraw this one. So if I shift this by 1, okay, so this I've shifted it by 1, and now if I shift it down by half, now if I shift it down by half, do I get the same result as this one? Yes, I get the same result as exactly this one. So let me redo this thing. So what I want to do is, so this means g of t. This means g of t is x of t minus 1. So when I shift it to the right, it's x of t minus 1. And when I subtract the average value, which is half, and when I subtract the average value, I get this waveform, right? Right? Good. So if this is the case, what is the Fourier? So now I can invoke the linearity property. So Fourier series here, Fourier series here, Fourier series here. So what is the Fourier series of a constant? Obviously it's a constant. So minus half, the Fourier series is minus half for k equals to 0 and 0 else, right? Because this is constant. If this is the case, then this is bk. So bk is, and this one I time shifting means I introduce a phase. So this will be ak e minus j k omega naught. This is t naught. This is t naught e minus j k omega naught, where x of t minus t naught, the Fourier series is ak e minus j k omega naught t naught, right? So this is the case. This is the case when k is not equal to 0, and when k is equal to 0, this would be ak a0 minus half for k equals to 0. And if you look at this waveform has no DC value. The average value, which is simply the area under the curve, average value is 0 because we have positive here and we have negative here. Okay, so positive and negative areas cancel, so obviously this is 0. So average value is 0. So what is bk then? So bk is simply 0 for k equals to 0, and when k is not equal to 0, this is sine k pi by 2 over k pi into e minus j k. And what is omega naught? Omega naught is pi by 2, right? Omega naught is pi by 2, e minus j k pi by 2. And let me write this one on this side. So k equals 0, k naught equals to 0. Okay. Good. So let's look at another example. Again, in this example, I don't want to use the analysis equation. I have a triangular waveform now. So if I have a triangular waveform, and triangular waveform is smoother than the square waveform. So obviously, the coefficients are going to decay as 1 over k squared. So let's see whether this happens or not. So I have this waveform. This is some x of t. I have this triangle over here, and I have the same triangle over here. Okay, good. Seems all right. This is 2. This is minus 2, minus 4, 0, plus 4, goes over here, goes here, so it repeats. And again, this x of t, the Fourier series here, and this height is 2. This height is 1. This height is 1. Slope here is half. Slope here is minus half. Right? And this is AK, and we want to find what is this AK, or maybe we call this EK. This is some EK, and we want to find what is this EK. Again, we cannot use the analysis equation. So if I differentiate this one, so I say G of t is d by dt of x of t. So if I differentiate, I'm just taking the slope. So slope here is positive half, slope here is negative half. So if I redraw this one, do you think this will be exactly the same as this one? So let me get this thing. Let me copy this one, copy, and then let me paste it over here. So paste here and move it up over here like this. Okay. So if this one, my claim is this is g of t. Why? From 0 to 2, the slope is half. So from 0 to 2, the slope is half. From 2 to 4, the slope is minus half. 2 to 4, the slope is minus half. So actually g of t is d by dt of x of t. And I know also this thing. If this is the Fourier series, if this Fourier series is, what is g of t? G of t Fourier series is some, what did I call here? Bk. So if this is bk, so bk is simply jk omega naught, right? The derivative property, jk omega naught, and x of t has Fourier series coefficients ek. X of ek. But what is bk? Bk we know is 0 for k equals to 0, and otherwise this is sine k pi by 2 over k pi into e minus j k pi by 2 for k not equals to 0. Right? Let me recheck. So sine k pi by 2 over k pi e minus j k pi by 2. E minus j k pi by 2. Okay, good. So so this is bk. So what is ek? So this implies ek is simply bk over jk omega naught. But what is omega naught? Omega naught 2 is pi by 2. So this is bk over jk pi, and I put a 2 over here. Okay. And obviously this function has a DC value. this function has an average value. So this is the average value. So what is this average value? So E0 is, this is the average value. And the average value is simply the area in one time period. Area under the function in one time period. So what is this area? So if I look at this area, and I'll just twice it, I'll just multiply by 2. So this area is half into base, which is 2, into height, which is 1. So this is simply 1. So E naught is 2 times 1, 2 times because this one, and this one. So it's twice here. So this is also 1. So area is 1. So 2 times 1 into 1 over t. And what is t? T is 4. So t is 4 over here. So 2 over 1 over 4, and this is half. Okay. So EK is this one, or this implies this is equal to half for k is equal to 0. So EK is half of k is equal to 0, and otherwise this is, so if I just put in these values, plug in these values, so this will be 2 here, sine k pi by 2, I'll have E minus j k pi by 2, because this is shifted, this is not centered around 0, this is for k not equal to 0, divided by this k pi, so this will be j into k pi squared. Actually, I can take this j pi up in the numerator. I can get rid of this j pi, and I can put here E minus j pi, because E minus j pi by 2 is minus j by Euler's identity. This is cosine of pi by 2 minus j sine pi by 2. So obviously this is 0 and this is 1. This is 1, so this is minus j. So this plus 1 over j is actually minus j, so this is E minus j pi by 2. Maybe I write it clearly. Here. So this is E minus j pi by 2. This is for k not equal to 0. This is for k equals to 0. Now you can see your coefficients. So from here you can see your coefficients. So EK's decay as 1 over k square. So EK is decay as 1 over k square, and this is what I told you before. You have this function which is much smoother than the square pulse, but when you differentiate this one, you get this one. So when you differentiate this one, since you get this one, so from lecture 2, your coefficients decay as relative to the derivative, which is discontinuous. Since this first derivative is discontinuous, so your functions decay as 1 over k square. Here the function itself was discontinuous, which means the 0th derivative is discontinuous. So the a case for the square pulse decay as 1 over k, but the a case or the Fourier series coefficients for the triangular pulse decay as 1 over k square, because its first derivative is discontinuous. Okay, good. Now we want to find the coefficient. Now I want to find this result. Which is the result for the this result for the square pulse. I want to find this using the properties. So I don't want to use the analysis equation, but I want to use the properties. So the first example, I want to resolve the first example, but without using the analysis equation. Okay, so let's see, how do I do that? So before that, let me find the Fourier transform of a pulse of an impulse, Fourier series of an impulse train. So this is an impulse train. X of t, height, if the area is 1, 0, t, minus t. This is an impulse train. X of t is an impulse train. So what is the Fourier series coefficients here? So x of t is k delta of t minus kt. If I take the Fourier series here, so this is ak. So ak is 1 over t. So I integrate from this one to this one. So minus t by 2 to plus t by 2, or I can integrate any impulse, doesn't make a difference. So this will be delta of t e minus j k omega naught t dt, the analysis equation, and this will become by shifting theorem. So by shifting theorem, so if I apply the shifting theorem here, so t is equal to 0, so e raised to power 0 is 1, so this is 1 over t. So my Fourier series coefficients are 1 over t. So this is constant. Okay, good. Now I want to calculate. So this is my original. Maybe I don't want to redraw this one. Let me copy it from here. So let me copy this from here. So it's this function. So if I copy this whole thing, let me copy this thing. Copy and paste. And I redraw this thing over here. And let me just do some cosmetic changes. Get rid of this thing. Get rid of this one, all these things, because this is actually not this wasn't the first one. So this is some g of t. This is t1. This is t. This is minus t1. This is minus t, and so on and so forth. Okay. So this is, so I want to find the Fourier series coefficients here. And I know what are the Fourier series coefficients here. Let's say this is some ck. So I want to find this one. And I don't want to use the analysis equation. I know that ck is, so from example 1, I know ck is actually 2t1 over t for k equals to 0, and this is equal to sine k omega naught t1 divided by k pi, I think, when k is not equal to 0, right? So we know this thing. So I want to calculate this one. So I want to recompute this one using the properties. So what if I take the derivative of g of t? So if I take the derivative of g of t, so d by dt, g of t is some q of t. This is some q of t. So what is this derivative? So this derivative is, so when I differentiate this one, doesn't look, it's a straight line. So when I differentiate the square pulse, I will get impulses on the edges, right? I'll get impulses on the edges. So this impulse going up, this edge going down. So I have impulse going up here, impulse going down here, impulse going up here, impulse going down here, impulse going up here, impulse going down here, so on and so forth. So, excuse me. This is q of t, and this one is at minus t1. This is at plus t1. This is obviously t minus t1. This is t minus t1. This is t plus t1. This is minus t minus t1. This is minus t plus t1. So this q of t, I can write this q of t as a sum of two impulse trains. So q of t is actually a sum of two impulse trains. And if this is my impulse train, this x of t, so if I shift it to the right by t1, and I invert it, or if I advance it to the left by t1, and then I leave it as is. So q of t is simply x of t plus t1 minus x of t minus t1. Is this right? So this pulse, this this impulse train. So this impulse train, let me copy this one here. Copy, and then let me paste it here. So if you look at this figure, and compare this one with q of t. So if I shift it to the left, which simply means x of t minus t1, to the right, so this will be at t1, this will be at t plus t1, and this will be at minus t plus minus, this will be minus t plus t1, minus t plus t1, and so on and so forth. Let me get rid of this one. So this is x of t minus t1. If I shift and if I negate it, I'll get these ones. I'll get these, right? t1, t1, t1 at minus t plus t1, and so on and so forth. And if I shift it to the left, obviously I'll get this one, I'll get this one, and I'll get this one. So this equation seems all right. So if I say that the Fourier series coefficients here are some ck, bk, dk, are dk. So what is this Fourier series coefficient? So this is either Fourier series coefficients here with the time advance property, Fourier series here with the time delay property. So this will be xt has Fourier series ak. So this will be ak e plus j k omega naught t1 minus ak e minus j k omega naught t1. So we have used the time shifting property here. But what is ak? Ak is 1 over t. So this is simply e j k omega naught t1 minus e minus j k omega naught t1, and this is this is divided by 2 and multiplied by 2. So this is simply 2. This is simply 2 sine k omega naught t1. Okay, so dk's are 2 sine k omega naught t1. So this is dk, and how is dk related to gt? So this implies the Fourier series coefficients here. So jk omega naught, the ck equals, so jk omega naught ck equals the Fourier series coefficients of qt, which we called dk, right? This we called dk. So this implies ck is simply dk divided by jk omega naught. Dk divided by jk omega naught. Okay, and this one actually I should have a 2j here. I should have a 2j here. There's a 2j here. So what is ck? So ck is dk divided by jk omega naught. Jk omega naught, and there should be a t here too. So ak is ak because ak is 1 over t. So there should be a t here too. So there is a t here, and then there is a t here too. Okay, good. So what is ck? Ck is simply 2, this j, 2j divided by j. So this is cancels, sine of k omega naught t1 divided by this t, this k omega naught t. So this k omega naught t is simply 2 pi, and this 2 cancels with this 2, and I'm left with this is equal to sine k omega naught t1 divided by k pi, which is the same result as before. So sine k omega naught t1 over k pi. Sine k omega naught t1 over k pi. And what is the DC value here? So DC value is still simply this area. So this area is simply 2t1. This area is 2t1. So you don't need any calculus here. So this area is 2t1. So C naught is actually 2t1 divided by t for k equals to 0. So this is ck. Right? So this is exactly the same as the first example that we did. So we can actually either use the analysis equation, or if we know the properties, how to use the properties, we can easily do that using this. Okay. So let's move on to the Fourier series for the discrete time case, which is exactly similar to the Fourier series for the continuous time case, except one or two fundamental difference. So Fourier series representation of discrete time periodic signals. Okay, so the first fundamental difference is the Fourier series representation, the Fourier series representation for discrete time periodic signals is a finite series. And why is it a finite series? Is a finite series because the number of distinct complex exponentials, because the number of distinct discrete time complex exponentials is finite. This is from chapter 1. Exponentials is finite. There are no convergence issues. There are no convergence issues in this case. So there are no Dirichlet's conditions that need to be satisfied, and Fourier series in Fourier discrete time Fourier series is equal to the Fourier series representation for all n. Okay, so is a finite number of distinct is finite. This is chapter 1. So go visit chapter 1 if you have forgotten this thing. So what is the linear combination? So let's look at the linear combination. So I'm not going to derive the result, but just to show you. So linear combination of harmonically related complex exponentials. So it's exactly the same as for the development is exactly the same as for the continuous time case. So we are just going to just breeze through this thing. So just some basic things that you need to recall. X of n is periodic with period n if x of n equals x of n plus n, where this is the fundamental period, and the smallest positive fundamental period, and is smallest positive integer. Okay. What about ej omega n? So ej omega n, where omega naught is 2 pi by n, is periodic with n provided if omega naught over n, omega naught over 2 pi is probably mn, right? Omega naught over 2 pi is m over n, right? So this is a rational number. So this is not periodic for every omega naught as in the continuous time case. So this is a rational number. So this is the first difference between continuous time and discrete time complex exponentials. So this is not periodic for all omega naught. This is only periodic if omega naught over 2 pi is a rational number. Okay. And then your family of complex exponentials phi k of n, which is e j k omega naught n. This is the set of discrete time complex exponentials with period n, right? And this one the is equal to e j k omega naught is 2 pi by n. So over there we had 2 pi by capital T. Now we have 2 pi by n. This goes on for k equals 0. Does it go on for k is equal to 0 plus minus 1? No. So this goes on. Let me see. So I write it here. So, or maybe I write it here. So k is equal to 0 plus minus 1 and so on and so forth. But we'll just see. So this phi k of n, these are periodic. They are only a finite distinct complex exponentials. These are periodic. They are finite distinct complex exponentials. The fundamental frequencies are, so the fundamental frequencies which are the same. So this is the second difference. They are finite. So this is the second difference between continuous time and discrete time complex exponential. So this is not going to go up to infinity. So this is not true. So these are finite distinct complex exponentials. Fundamental frequencies are, frequencies are probably multiples of 2 pi. So fundamental frequencies are multiple of 2 pi over n. So frequencies are multiples, which is the same, of 2 pi over n. It was 2 pi over t, and there are only n. So since this is finite, only n distinct complex exponentials, only n distinct discrete time complex exponentials. So this sum is going, so this k goes up to this n. Okay, and why is that? So let's see here, and actually we looked at this in chapter 1 too. So note phi k n equals phi k plus r n. So if I instead of k, I have k plus rn here. So if I replace this k by this k plus rn, since omega naught is 2 pi by n, I'll have ej 2 pi omega, I'll have ej 2 pi m, and obviously this is 0. So this will be ej k plus rn into 2 pi by n into n, which is equal to ej k 2 pi by n into n into ej n cancels, ej 2 pi rn, and this is equal to 1 because this says integer. So this goes in multiples of cosine 2 pi, and this is equal to phi kn. So we have only distinct complex exponentials. If this is the case, so k is changed by only integer multiples of n. So this implies k is only changed by integer multiples of n. So k is only changed by integer multiples of n. So scale is only changed by integer multiples of n. So your discrete time Fourier series. So discrete time Fourier series is x of n equals ak ej k omega naught n. So this is omega naught, and this is omega naught. So over there we had e j k omega naught t, and this k is only n distinct complex exponentials. So this is same as we said this one over one time period. So this simply means this is only n distinct terms, only n values of k, whatever those values are. So this is only n, because this is, you will just see why, because this is periodic. Okay, so this is ak. So this is the synthesis equation. This is the synthesis equation. This one is a synthesis equation, and we note this x of t is discrete in t and periodic in t. So this discreteness should imply this ak should be periodic in omega. Again, this k is k omega naught. So k implies k omega naught. So always remember this k is actually implying k omega naught. So that's where the frequency comes in. And this periodicity implies this is discrete in omega. So this is the basic difference. So this is different from the continuous time Fourier series case. This is different from the continuous time Fourier series case. Why? Because over here, this was continuous in continuous time Fourier series. This is discrete. This is not, I don't think so. We should do t, we should do n. Discrete in n, and similarly periodic in n. Okay. Right, so we have to see this one. So how can we say if AKs are periodic? This we have to prove. Need to prove this. But this shows your AKs. So as opposed to continuous time Fourier series, these AKs are periodic. So this is the fundamental difference between the continuous time Fourier series and the discrete time Fourier series, that your Fourier series coefficients are periodic. So maybe I write it in bold here. So Fourier series coefficients of discrete time periodic signal are periodic, right? Okay, and how do we prove that? So let's prove this. So how do we determine the Fourier series representation? So determination of Fourier series representation of a periodic signal. Okay, so given xn, x of 0 is simply some values of k, ak. This is the average value, obviously. x1, average value of the spectrum, I guess. x1 is k equals n, ak ej 2 pi by n k, right? Because n is equal to 1, and so on up to x of n minus 1, because these are only n terms here, x of n minus 1 k n, I'm sorry, these are n terms. Why? Because this xn is periodic. So xn is periodic. This is periodic. Okay. So xak ej 2 pi by n into n minus 1 into k. Okay. So we have n linear equations and n nodes. So these are n linear equations, in n unknowns, Okay. So just the same way we did we found the analysis equation for the continuous time Fourier series, we're going to do the same thing. So let's, but before we do that, you need to figure out this identity. What is this equal to? N terms. So sum of n terms, ejk 2 pi over n into n. What is this equal to? So how do you prove this? So what is this equal to? So tell me, what is this? N is equal to 0 to n minus 1 ejk 2 pi over n, and then I do like this. So this is kind of a geometric series. If this is geometric series, so this will be 1 minus this term raised to power upper limit plus 1, which is n. So n cancels, and I have ejk 2 pi. And then I divide this by 1 minus ejk, the summand 2 pi by n. Okay. This is not equal to 1. This is not equal to 1 since k is not equal to 0. K is not equal to 0 or any integer multiple of n. Since k is not equal to 0 or any integer multiple of n. Okay, so this is not 0. So if this is not 0, what is this equal to? This obviously is equal to 1. If this is equal to 1, this goes to 0. So this summation is equal to 0 when your k is not equal to 0 or some multiple of n, right? Some integer multiple of n. And when this is equal to 0, this is equal to integer multiple of n, then what happens? So if this is equal to 0, obviously e raised by 0 is 1. We have only n terms here, so this is equal to n, right? So when k is equal to 0, this is e raised by 0, which is 1. So it's a constant 1. So 1, when you add from 0 to n minus, there are n of these, so that's why this is 0. So this means sum over one period. So this is the sum over one period. Sum over one period of values of a periodic complex exponential. So sum over one period of values of a periodic complex exponential is 0. Complex exponential is 0, given this thing, unless that complex exponential is a constant. Unless that complex exponential is a constant. Exponential is a constant. Okay. So keeping this in mind, so this means, so if I have x of n and I multiply e minus j or 2 pi by n. I multiply this on both sides, so I have k n terms. So this is x of n, ak e plus j k 2 pi by n into n, and then I multiply this one over here, e minus j 2 pi by n r n, and then I sum this up. Just like I took the integral, and I sum this up over n terms. If I sum this up over, I sum this up over n values. So I sum this up over n values. So when I do that, so what do I get over here? So this one is simply equal to this summation, n equals, so summation over n, summation of k over n values, ak e plus j k minus r 2 pi by n n, right? So, and what is this equal to? And this term, so I can always interchange. So I can always interchange these two. So if I interchange these two, so if I interchange these two, so this becomes k, and this is n, ak comes out, this is ej k minus r 2 pi by n n. This thing is exactly the same as this thing. This thing is exactly the same as this thing. So ej, so this will only have value. So this is equal to n when k equals r, sorry, k minus r, when k minus r equals 0 or plus minus n, and so on and so forth, and it's 0 else. Right? So when k is equal to r, there is only one term here. There is, when k is equal to r, there is only one term in this sum, and that is ar. So this implies, so this is n times ar because this is n here. So this implies ar equals 1 over n terms xn, because xn is periodic, e minus j 2 pi over n r. But r is a dummy variable, so I can always get rid of this r. I can have this k because this is this equation here, which I've brought it down, and this becomes again k. So this equation is my analysis equation. This is my analysis equation for the discrete time Fourier series case. Okay, so and now how do we show that this is periodic? So how do we show this is periodic? So this is simple. So to show this is periodic, we say if 0 is less than equal to k is less than equal to n minus 1, if this is true, then x of n is a0 phi 0 n plus a1 phi 1 n, where phi kn is where phi kn is ejk omega naught n. So these are discrete harmonically related complex exponentials, plus an minus 1 phi n minus 1 n, right? And for 1 is less than equal to k is less than equal to n. So if I take a different n values, so if I take different n values, I'll get x of n, the same x of n. This is equal to a1 phi 1 of n plus a2 phi 2 of n plus an phi n of n, right? But this xn is equal to this xn. All these are the same, so the only difference is this one and this one, but phi nn and phi 0n are the same. However, phi 0n is the same as phi n. This implies a0 equals an. So if this is true, so in general, ak equals ak plus n. So this implies Fourier series coefficients are periodic. Fourier series coefficients are periodic with n. This is the biggest difference between the Fourier series. So in continuous time Fourier series, AKs are not periodic. So this is the biggest difference between the two, and we can actually prove it here too, because if I change this k to k plus n, so if I do this k to k plus n, if I do this change k, so this I'll still get an exponent which is this one times an exponent which evaluates to 1. So I can actually prove from here that these are also periodic. So AKs are periodic, and AKs for the discrete time Fourier series are periodic. These are periodic. Why? Because this is a discrete time complex. This is a discrete time signal, and the complex exponential are not infinitely many. There are only n distinct discrete time complex exponentials. So I'm not going to find the prove the properties. So the only properties that are different, so properties of discrete time Fourier series that are different of discrete time Fourier series, different from continuous time case. I'm going to list them, and I'm not going to prove them. You can prove them yourself. Different from continuous time Fourier series. So what are these properties? So these properties are multiplication. The first one is multiplication, and there is no derivative. There is the first difference. So multiplication. So what happens in multiplication? So if x of n has a Fourier series coefficients ak, and y of n has Fourier series coefficients bk, then z of n, which is x of n, y of n, has Fourier series coefficients ck. And what is ck? Ck is simply ak into b into k minus l. So tau into t minus tau. I think tau. This should be l. This should be l. Tau into t minus tau, right? And l over n. And this is, by the way, periodic convolution. Over there, this was aperiodic. Now this is periodic convolution. Why periodic convolution? Because AK and BK are periodic. AK, BK are periodic. This was not the case for the continuous time case, continuous time Fourier series. The second difference, so the second difference is in the first difference. There is no derivative definition. So the first difference. So what is the first difference? First difference is, so x of n has the Fourier series ak. What is x of n minus x of n? This is the first difference. So the first difference, this is some y of n. This has a Fourier series bk, and this Fourier series is simply ak minus, just in the case of just in the continuous time case, this is ak e minus j k omega naught, and this is n naught. So this is n naught, so n naught is 1. So we have ak e minus j k omega naught, which is simply equal to ak into 1 minus e minus j k into 2 pi over n. Okay. And there is no difference in the Parseval's theorem. The only difference is it's a finite sum. It's not an infinite sum. So in the Parseval's theorem, you still calculate the power. Nothing has changed there, but the only thing that has changed is in the finite sum. So here this is over n samples, over n samples. Over there, I think that was infinite. So this is only over n samples. And in the Parseval's theorem case too, if x of n has a Fourier series ak, so this implies 1 over n. So again, if I want to find the average power, x of n absolute square. So this is the average power in n, average power in n. It's time or n, it's one and the same thing. This is equal to instead of infinite, there was what was there actually this there was an integral here which was periodic, which was over one time period, and this sum was over from minus infinity to plus infinity because AKs were not periodic, but since AKs are periodic, we only do over one period instead of, so this is average power in spectral domain, average power in spectral domain. And the only difference was in this sum. For the continuous time Fourier series case, this sum is infinite. Sum is it's an infinite sum. This is an infinite sum. In that case, this goes from minus infinity to plus infinity. So this is the difference here. So now this is only over n values. So versus the continuous time Fourier case where we had the infinite sum. Okay, so let's look at some examples. So let's look at, I think I have 2 or 3 examples. So the first one is exactly the same as for the continuous time case. So we have x of n equals sine omega naught n. Again, this is periodic only when omega naught over 2 pi is m over n is a rational number. So if this is not the case, then this will not be periodic, unlike the continuous time case, which is periodic for all omega naught. So again, if I apply the Euler's identity, so this is equal to Ej omega naught n over 2 j minus E minus j omega naught n over j2. So same case here. This is from Euler's identity. So from Euler's identity, and you don't need to use the analysis equation here because you can simply see this by observation. So here this implies A naught is 0, A1 is 1 over J2 because this is omega naught, and A minus 1 is minus 1 over J2. Same condition holds. So if x of n is real, so if x of n is real, this implies AK equals A conjugate minus K, or A conjugate K is simply A minus K. So this is simply the conjugate of this one, and obviously this is a real signal. And this is not the only case. So A1 is actually equal to AN plus 1 and so on and so forth. And this is equal to AN minus 1 and so on and so forth. So these are periodic. This is the difference here. So these are periodic with n. Okay. What about the second example? The second example is also the same as the second example for the discrete time case. So x of n is 1 plus sine 2 pi by n into n plus 3 cosine 2 pi by n into n plus cosine 4 pi by n into n plus pi by 2 and so on and so forth. So this I can write as, again using the Euler's identity, 1 plus Ej 2 pi by n, this is omega naught, 2 pi by n over J2 minus E minus j 2 pi by n over J2 plus 3 by 2 Ej 2 pi by n over n plus 3 by 2 E minus j 2 pi by n over n. And for the last one I have this is 2 omega naught. This is 2 into 2 pi by n. This is 2 into 2 pi by n. So this is Ej 2 into 2 pi by n omega naught n into Ej pi by 2 over 2 plus E minus j 2 into 2 pi by n into E minus j pi by 2 over 2. So if I collect them, so this implies, and this also, this is equal to an, this is equal to an, and so on and so forth. So a naught equals an equals 1, and obviously 2n and so on and so forth. And a1 equals an plus 1, and so on and so forth. This is equal to 1 over j2 plus 3 over 2. And a minus 1, which is equal to an minus 1, equals 1 minus 1 over j2, this one, minus 1 over j2, and plus 3 over 2. And again, this is the conjugate. These are conjugates. These are conjugates because it's a real signal. Conjugates because x of n is real. Okay. And then a2 is equal to an plus 2 equals, so a2 is simply half ej pi by 2, because this is 2 omega naught, and a minus 2 is equal to an minus 2 equals half e minus j pi by 2. Again, these are conjugates. These are conjugates. Why? Because x of n is real. Okay. And ej pi by 2, by the way, e plus minus j pi by 2 is simply plus minus j. Note, this is simply plus minus j. Okay. You can always plot the magnitude spectrum and the amplitude spectrum, and you'll see that the magnitude spectrum is even and the phase spectrum is odd. Okay, and what do we want to do next? So one more example before we sign off. So example 3. So you have this square pulse train in the discrete case. Okay, so now we have a square pulse train in the discrete case, and I will just quickly redraw this one. So this is 0, this is n1, this is minus n1, same notation. This height is 1. This is the height, this is not the area. And let me just quickly copy this one, copy, and then let me paste it. Paste here. And then paste here again. Paste here and get rid of this one. This should be all right. Let me move it a little. Okay, so let me relabel it. So let me quickly relabel this one. This is n. So over here, this is broken. This is n. This is n minus n1. This is n plus n1. This is again minus n. This is minus n. This is minus n minus n1. This is minus n plus n1. This is minus n plus n1. So we are only interested in one period. So if we are only interested in one period, what is a k? So a naught, or maybe ak. So ak where or maybe a naught and then an. So a naught, an, and so on and so forth. This is simply equal to 1 over n, and I simply add these up. So simply add these up. So this is how many? These are 2n plus 1. This is 2n1 plus 1. So this is my average value, and this is equal to ak for k equals 0 plus minus n plus minus 2n and so on and so forth, right? Okay, good. And ak, maybe I just write a naught here. And this is equal to ak for, okay. And ak equals 1 over n values. So n non-zero values over one period. So maybe I write the equation first. X of n e minus j k 2 pi by n n. Okay, and this is equal to 1 over n. The non-zero values are from n is equal to minus n1 to plus n1. X of n is 1, and we have e minus j k 2 pi by n. And let me write it like this. So I can apply the geometric series. Okay. So if I do that, so what is this equal to? So, and let me do a change of variable here. So let m plus n, let m is equal to n plus n1. If I do that, so this will become 1 over n, and this will be a sum. When n is equal to minus n1, m is equal to 0. And when it's this one, this will be equal to 2n1. This will be e minus j k 2 pi by n here, and this n becomes m minus n1. So m here and n minus n1 means I take it out, e minus j k 2 pi by n n1. Okay, right? Okay, good. So I have e minus j k 2 pi by n into n1 outside divided by n, and inside this is a geometric sum. So this is 1 minus e minus jk 2 pi by n, and this is 2n plus 1. This is 2n1 plus 1. So upper limit plus 1 divided by 1 minus e minus j k and the summand 2 pi by n. Okay, and here I want to just use one trick. If I take this 2 outside, I'll just put a half here, right? I'll just put a half here. And why I want to do this? Because whenever you have some ejx, you can always write this ejx as ejx by 2 into e minus jx by 2. So this is the half angle expansion. So whenever you have ejx, so always you can always write this as ejx by 2 and e minus jx by 2. If this is the case, so I can write this one over here. So this implies ak equals e minus jk 2 pi by n into n1 over n. This one, if I take out half angle, this will become e minus jk. So 2 cancels, and this will be, or maybe I write k over 2 into 2 pi by n, right? So this would be then here ejk over 2 into 2 pi by n minus e minus j k over 2 into 2 pi by n. If we do that, so if I multiply these two, obviously e minus jk and with this exponent is the same. So e minus jx into e plus jx is 1. And when I do e minus jx by 2 into e minus jx by 2, obviously I get this term over here. And over here, I take out e minus jk 2 pi by n into n1 plus half. If I take, because this is already 2, so if I take this half out, I'll have ejk 2 pi by n into n1 plus half minus e minus jk 2 pi by n into n1 plus half, right? Again, same trick over here. So now I can see this is a sine, this is a sine, this is also a sine. So I can write this as sine k 2 pi by n into n1 plus half divided by, this is sine 2 cancel, sine pi k by n, sine pi k by n. There is this 1 over n over here. What about this one, and this term? So if you look at these terms, 2 pi k over n is common. So here this term gives you, so just look at the exponent. So look at exponents. So look at exponents. So exponents or coefficients of exponent. Look at coefficients of 2 pi by n k in the exponent. If I do that, so what do I have? I have minus n1, okay, minus n1 from here. Here I have minus n1 plus half, right? And over here, this when this goes into the numerator, this is plus. So 2 pi by nk, this is plus half. So minus half cancels with plus half, minus this should be a plus actually. I think this is a plus. This should be a plus. This is not a minus. I'm sorry. This one is a plus. When I do, so this one is when I do m is equal to n minus n1. So when n is m minus n1, this is a plus here. This is a plus here. I'm sorry. This is a plus. So this is a plus. So this is a plus. So plus and minus n1 cancel, and then minus half plus half cancel. So there is no term, and this is ak, and this is equal to. So this is equal to when k is not equal to 0 plus minus n and so on and so forth, and this is equal to 2n1 plus 1 over n when k equals 0 plus minus n and so on and so forth, right? Okay, good. So let's just do an application of this one. So let's do an application of this. Suppose we have this function. We have this function. This is a function. So we have minus 1, 0, 1. So this height is 2, minus 1, 0, 1. Then we have 2, 3. Then again we have 4, 5, 6. So 2, 3, 4, 5, 6. This height is 1. And this repeats, same here. So minus 1, minus 2, minus 3. And then I have minus 4, minus 5, minus 6. And then this repeats. So minus 5, minus 4, minus 6. So this is x of n. Okay. So I want to use the above result to calculate the Fourier series of this one. This I can write as a sum of two signals. So this is plus this one and plus this one. So one of the signals is actually minus 1, 0, 1. Nothing here, nothing here. Then I have this one, I have this one, and I have this one. And nothing here, nothing here. And this height is 2, nothing here, nothing here. And this one, and this one. Obviously, this is extended. You extend this one. There's a problem with this pen. Okay, so this is 0, 1, 2, 3, 4. This is 5. This is minus 5. So n is 5. So n is 5. So let's say this is x1 of n. This is x1 of n. And now I have x2 of n. x2, or maybe this is not 2. This is 1. So I have 1, and then I have a string of 1s. Then I have a string of 1s over here. And this goes on here. This goes on here. And obviously, let me shorten this one. So this is 0, minus 1, 1, 2, and so on and so forth. This is x2 of n. Again, this height is 1. So if I add these two, I will get this one, right? Because when this is 0, this will be only 1. And when this is not 0, this will add and we'll get a 2. Okay, so what is x1 of n? The Fourier series of this one is some bk, and this bk is 1, 2, n plus. So n, what is n1 here? So n is 5 and n1 is 1. So 2 plus 1, so it's 3 by 5, right? It's 3 by 5 for k equals to 0, plus minus 5, and so on and so forth, right? And otherwise, this is sine. And what is this sine? This sine 2 pi by 5 and this is 1, so 3 by 2. So 3 by 2, so 3 pi by 5. Sine k 3 pi by 5. Sine 3 pi k by 5 divided by sine pi k by 5. It's pi k by n, right? Pi k by n, so pi k by n here. And this is for k equals not equal to 0, not equal to plus minus 5, and so on and so forth. Okay, and what about x2n? So x2n, the Fourier series is simply ck, and ck is 1, so it's 1, it's 1 over 5, it's 1 over 5 for k equals to 0 plus minus 5, so on and so forth. I can take n equal to 5 over here, so, and this is 0 else. So this is a constant, so obviously. So when I add them up by the linearity property, so x of n has the Fourier series ak, which is equal to bk plus ck, or this is equal to simply 1 over 5 plus 3 over 5. I'm sorry, this is not 1 over 5, this is simply 1. This is not 1 over 5. This is simply 1 because this constant is 1. So 1 plus 3 over 5, this is 8 over 5. This is for k equals 0 plus minus 5, and so on and so forth. Or otherwise, this is simply sine 3 pi k by 5 over sine pi k by 5, and this is for k not equal to 0, not equal to plus minus 5, and so on and so forth. Okay, and why is it this 1 equal to? So this is 1 because 1 over 5, I can take any values, n is equal to 0 to 4. This height is 1, so this is 5 values. So this is 5 over 5, which is equal to 1. And obviously, since this is a constant, obviously I'm going to take this value. This is the DC value over here. Okay, so this is all we want to do from for regarding the development and the examples of the discrete time Fourier series case. Again, if you have any problems, you can send me an email, or we can discuss this further on Mondays. Okay, so I'll see you on Monday, if not before. Thank you.